you think?
You know, I tend to think so. So I'm very excited that we both get to bring Brandon Berry to the stage. Brandon is the CEO of Black Harbor Cybersecurity, and he's going to tell us a little bit more about these things. And, you know, it doesn't matter if you're an OEM or if you're a supplier, you need to get comfortable with these security terms, particularly the things in 21434. And in this conversation, Brandon is going to help us walk through each type of testing, what it is, and how to get it done. So, Claudia, I think without further ado, we can kick it over to our good friend, Brandon.
Yeah, take it away.
Claudia, Jen, thank you guys so much. You guys are amazing. And thank you, to everyone at Geneva who helps kind of organize this. These conversations are really important to have, and really grateful for the team that's involved with the security team here at Geneva. Really keeping the conversation moving forward. And Chad, thank you for your presentation. Really enjoyed it. All right, let me figure out how to move this forward. So yeah, today I'm going to be talking a little bit about security testing within the context of the standard and regulation that we all hear a lot about, 21434, and then this UNR 155. A little bit about what I'll walk through. I'm going to be brief on the overview of 21434 and UNR 155. I know you guys have been through that overview probably 10 times in this series itself. It's a big deal. Everyone's trying to figure it out right now. I'll be talking specifically about testing as it relates to 21434 and then WP29, and then just a solution that we're working on to help make that more effective and efficient based on our years of experience in the space. So a little bit about me. If you don't know me, I'm the founder at Black Harbor Cybersecurity. We're a company based in Detroit, Michigan. We've been in business since 2014, kind of this working with, we do a lot of work with Fiat Chrysler, now Stellantis, in response to the incident that shook the industry. So I've been running that for some time. I'm the Americas lead of a nonprofit group called the Automotive Security Research Group, or ASRG. You should check the videos out on YouTube because there's a ton of really interesting content that we've had presenters from all over the place presenting. It's a pretty big global organization that I've been really excited to lead the Americas chapters, but there's over 40 chapters around the world. You'd be shocked that people all over the world are interested in this topic of automotive security. I just find this fact interesting. I was one of the youngest full CISSP holders when I got it at 23. It really kind of points to the fact that this industry is hard to get experience at a young age in. A lot of people talk about the workforce issue in the space. And I just found it interesting. It's one of these certs that maybe a lot of companies ask for in somewhat entry-level positions, yet you need 5 years of experience to get it. And I was just able to do that at a pretty young age. And then, Chad was speaking a little bit about car hackers. I myself have placed first place at DEF CON's Car Hacking Village back in 2019. A really fun competitive year. It was us, the Canucks, against teams from GM, other teams as well. The prize was a Tesla, so it was very, very competitive. So hopefully that organization and hacking competition gets up and going again as conferences pick up to be in person once again. And I encourage all of you to check out DEF CON out in Las Vegas. And then this big old hunk of junk here on the screen, my race car. I'm really passionate about cars. I do what is called drift racing. This is my car that I built and welded the roll cage in myself and really did everything. Love to get out there on the track. If that's something of interest to you, follow up, have a conversation with me, because once you get me started, I won't stop. Okay, but to get into the content you care about. In general, cybersecurity testing is critical within this process of vehicle cybersecurity. You know, Chad had a great kind of discussion about more the design and technical side, but at the end of the day, you really only get the security that you test for. There's a lot of moving parts that are involved with designing and integrating a secure vehicle. You know, you have requirements that fall out of your design process that go to a supplier. And a lot of times there's trust between that automaker supplier relationship, that those requirements were implemented correctly. A lot of moving parts. So that testing piece of cybersecurity for vehicles, uh, it's really that trust but verify model. You need to ensure that the controls that you designed into the vehicle are in place. And that's kind of what 21434 gives you. I mean, that's the point of the process. On the left side of the V model, you know, we're walking through defining security goals all the way to breaking that down into specific software and hardware requirements. You give that to the suppliers implement them with their technical expertise. They maybe define their own more detailed requirements if the automaker's security requirements are too high level. And then on the right side of the V, there's this kind of mixed responsibility between suppliers and automakers, where they really need to make sure that the end product actually is meeting those requirements. And so you're going through this verification and validation process. That's what this talk's going to be about. And just a minute about WP29. At the end of that design process, these automakers are going to submit for type approval to make sure that their vehicles are indeed approved to be sold in participating nations for this type approval process. Those auditors are going to look at the CSMS that is in place. Many of the automakers are referring to ISOSAE 21434 as their kind of backbone for their CSMS with a twist on it. But at the end of the day, these auditors are going to look at all the work products that the automaker has generated. Ideally, there's a testing piece of that. And then at the end of it, they get the certificate of compliance for a CSMS, this type approval stamp that goes on the vehicle type that then permits that vehicle to be sold in the participating nation. So just a second on how those two things fit together. It's kind of how I referred to a minute ago. The CSMS on the left is largely powered by ISOSAE 21434. There's also this piece of it that's about infrastructure security. Are you securing the back-end systems? You know, UNEC WP29 is not all about vehicle security. It's about photo security. It's about cloud security, making sure that there are mitigations in place to prevent threats from exploiting the cloud environment and moving laterally onto vehicles, because of course that makes sense. But a lot of times these automakers are organized in ways where you have product cybersecurity, the people responsible for the actual vehicle, and then you have cloud security, a totally separate group within the automaker. And oftentimes, you know, there's a interesting silo between those organizations. And then finally, organizational security is a key piece of your ISMS. You know, is the organization itself secure from things like insider attacks? The two pathways here for auditing are CSMS audits, or looking at the work products to make sure that the CSMS is indeed effective to securing their vehicles and their vehicle designs, and then this vehicle type auditor, or the actual specific review of a particular vehicle type that is being applied for type approval, so that that specific vehicle type is approved. Okay. So who are the players in this space? You know, I referred to a little bit. You have this kind of supplier tester. They're the ones receiving cybersecurity requirements from the automaker, usually responsible for more component level cybersecurity requirement verification and more component level cybersecurity goal validation. I choose those terms specifically from ISOSAE 21434. Now at the goal validation layer, I just want to point out the things that the standard points to: fuzz testing and pen testing, because oftentimes we start conversations with suppliers on that basis. Hey, we need to do fuzz testing, we need to do pen testing. We don't know why the automaker's asking for it, but we need to do it. Can you guys help us with that? So that's where that lives. Oftentimes, suppliers need to perform fuzz testing and penetration testing against their individual components. The next one over, the automaker tester. They're the ones that are operating that CSMS that I kind of referred to in the last slide. They're usually responsible for more of the integration, the vehicle level stuff, ensuring that as all of these components come together, the cybersecurity requirements at the vehicle level or system level or subsystem level are coming together in a way that matches their design process. And then it's that cybersecurity requirement verification and cybersecurity goal validation. Again, fuzz testing and pen testing often come up as the techniques for cybersecurity goal validation at the vehicle layer as well. And then the final tester, that vehicle type auditor. This isn't 100% clear, and I'll get to this a little bit later. But at the end of the day, these type approval auditors need to know that the vehicles they're putting their stamp of approval on are indeed secure. It's not going to be as simple as reviewing documentation and trusting that that documentation is accurate. We've seen a lot of nations already starting to put together their cybersecurity lab where they need help testing vehicles. You pull in a vehicle, you execute a set of security tests against it, and determine if it's meeting defenses for mitigations that, or defenses against threats, in other words, mitigations that are called out in the regulation. Okay, so those are our kind of actors in the space. So when do we test within this process? Supplier testing usually falls out of the requirements that are defined from the automaker. We'll get to what the suppliers need to do specifically, but it tends to look like functional and penetration testing. It'll be some set of requirements. One of those will look like you need to perform work products that show that you've done functional cybersecurity testing, and you need to show a third-party penetration test against a given component, or an internal penetration test. Really depends on the automaker if they really want a third-party set of eyes on it. From the automaker, again, they're integrating those components. So they're doing more of that system level testing. So within the V model, this is kind of after all the components have been designed, everything's starting to come together. They need to now ensure that the security and layers, kind of what Chad was referring to, ensuring that all of that comes together and ends up yielding a secure vehicle. And then finally, the type auditor. Eventually the automaker will apply for type approval, and they're doing that right before that vehicle goes into production. So let's dive into that. Types of testing. Functional testing. The latest version of ISOSAE 21434 calls it this kind of functional testing. This is a new term within the standard in the latest term. But what this generally means is that you need to, on the left side of the V, design your set of cybersecurity goals for the vehicle, break that down into a set of specific cybersecurity requirements. And then for each of those requirements, you need to have a verification specification. That means it tells the tester exactly how to test for a specific requirement to ensure that that requirement is being met. So typically how this looks, you need some kind of integration test bench to perform this test. Largely in the development stage, the earlier you test, the better, because if you find out that you're not meeting your requirements, you have to go back to the supplier, and no one wants to delay vehicle programs. So really, the earlier that you can ensure that you're meeting your requirements, the better. And typically at that stage, you're trying to get your hands on some kind of integration test bench so that you can ensure that that system is meeting its requirements. It's not yet a full vehicle that you can get your hands on. You execute that test specification and you document the results. That's the work product that auditors will want to see, and you do so for each cybersecurity requirement. I referred to it earlier a little bit, but like I said, automakers need to do this at their vehicle layer, but then also suppliers need to do it at their own individual component layer. There's these two kind of competing sets of requirements at different levels of technical depth. So I'll leave that one there, functional testing. And without getting too far into the details, I would encourage you guys to ask questions about where you have more interest in kind of guiding the conversation at the end of this, because I'm just going to stay at a high level to try and delineate between these different types of testing. So the next one, fuzz testing. This is one of those types of things that it's referred to in the standard. Everyone does it a little bit differently. It's an age-old practice. People have been fuzzing, I think the term was invented back in the 80s, and they were using it to fuzz command line parameters within Linux kind of command line utilities. This term that is stuck around because it's an effective way of security testing, but it's not defined on purpose. It's not defined because it is kind of a creative technique. Yet when you have a standard like ISOSAE 21434 refer to fuzz testing as a great technique, you now have a lot of people saying, yeah, we need to do fuzz testing without any specific definition about how that's done. So it makes it really confusing when a component supplier comes to us and wants fuzz testing performed, and maybe they're comparing us to another vendor and they're trying to figure out exactly who's better and why people are charging the money they are, and what exactly is being done. So I just wanted to talk about what fuzz testing is for a couple of minutes here. In general, fuzz testing, the intention of it is to find unknown vulnerabilities, whereas a lot of security testing is focused on finding known vulnerabilities, where that means that you're scanning for vulnerabilities that exist within databases like CVE. Fuzz testing is trying to find vulnerabilities that may exist that no one knows about. Zero-day vulnerabilities, if you will, insofar as they may be kind of your application layer vulnerabilities where you aren't doing proper parameter checking and a piece of fuzz input comes in and something crashes. What do we mean by fuzz? Fuzz is a piece of randomized data. If you look at this kind of graph on the right, you start with some initial vector at the very top. That initial vector is typically something that makes sense for the target system. Remember, we're using this term loosely, fuzz testing. You can fuzz an API, you can fuzz a vehicle, you can fuzz Bluetooth, you can fuzz Wi-Fi. Fuzzing is a concept. And so what we mean by initial vector is a payload that makes sense within a given system. In the case of CAN bus, you may use a payload that is a starting known payload within the DBC files that have been provided, and now you're iterating within some bounds to try and find payloads that may work, may get past some of the basic filters, but may cause some adverse behavior. So you start with some initial vector. You pass that through some kind of fuzzing engine, which there's plenty of open source ones, where usually they take some random number generator and they apply it to that initial vector in one way or another, such that you generate this piece of fuzz data. It's something that may include, random characters. It may include non-UTF-8 compliant characters. It's each fuzzing engine may do it a little bit differently for each different technology, but you get this piece of fuzz data, which is unexpected input. Now you just send that to the target and you ask, and then you look at the target's reaction to figure out, did something weird happen here, or did the target just reject it as anticipated? Then you use that fuzz that you just generated and pass that back in as your initial vector. That's typically how you're thinking about this, such that your fuzzing engine is now applying randomness to its previous piece of fuzz. And in this way, you let it run continuously, such that it is using randomness to guide it, and that the space of known inputs is kind of increasing to its limits, where you're testing inputs and payloads that would have never been tested by any security tester that's testing for known vulnerabilities. So that's what fuzzing is. It's not complicated. It's really simple. You could write your own fuzzer for a given technology really quickly. The challenge becomes making a fuzzer that makes sense for a system, because you can also write bad fuzzers. So I say that because I feel like there are companies and products out there that claim to do fuzzing for you, but oftentimes fuzzing has to be built by you. It has to be guided by the system owner or the product owner in order to be effective. And what that usually looks like, you have that same issue of acquiring that test setup. You need the component to test against in the first place. Uh, that's often the hardest challenge. You know, how do you get additional components or additional vehicles or vehicle test benches to test against? Once you have that, you then instrument the test interfaces. Whatever you want to test, whether it's CAN or Bluetooth or whatever, you need some test interface such that you can communicate with the given target. You choose those initial fuzz vectors in a way that makes sense for that given technology. You choose the conditions on which to log an unusual behavior of the target. That's typically the hardest part. How do you know that your payload caused an issue? You know, there are lots of different ways to approach this, from state machine approaches where you define the exact expected behavior, and anything outside of that is an unknown state, and use that as your trigger. But that's usually the hardest thing. You know, the most basic thing is you can monitor for a crash. And then, like I said, you start fuzzing with that initial vector, you run it for some defined period, and now you're looking through a ton of data to try and figure out, was there anything that was problematic? So hopefully that wasn't too repetitive, but I just wanted to talk about fuzzing as in terms of what it is, because oftentimes, you know, there are people, like I said, that use the term from the standard, but maybe don't have the kind of baseline knowledge about what to do in the first place. Another term from the standard, vulnerability scanning. This is the opposite of fuzzing. It is testing for known vulnerabilities. You typically, you are using some tool set to test a given system for vulnerabilities using a known database. Typically, we break this down between internal and external vulnerability scanning. Those are lessons or terms borrowed from IT security, where you're either scanning a server from inside, where you have credentialed access to the server, or you're scanning it from outside, where maybe you're just looking at it from what ports are exposed on that server. In the case of internal vulnerability scanning, there are lots of tools. This is a dynamic space within the vehicle internal vulnerability scanning realm, but you tend to need to know what are the softwares and hardwares that are running on a given target component or given target vehicle, SBOM or HBOM. That's a big topic to unpack within itself. And then you take those software versions and hardware versions and correlate those against known vulnerabilities that may apply. And now you're sorting through that or sifting through that to understand which ones actually apply. Because 95% of vulnerabilities that will be reported for a given set of software and hardware will not apply, because you aren't using the library in the way that the vulnerability could be exploited. That's internal vulnerability scanning. I say that because that's not complex either. So there are tools out there, but at the end of the day, it's going to be a lot of sifting through to figure out relevancy based on having a list of known software and hardware versions that you have. External vulnerability scanning tends to be the opposite approach. You know nothing about the system. Some people refer to it as black box or gray box, and you're now using some characteristics of the device, of the target, whether it's interfaces and technologies, to perform some scans using some tools to identify likely vulnerabilities. An example for CAN is there are UDS scanners that will go through each module that responds and perform a scan of UDS services that are exposed and identify if there are kind of exposed services that should not be exposed from a diagnostic standpoint. That's what we mean by external vulnerability scanning. So I'm not going to get into further technical detail about this, because guess what? ISOSAE 21434 doesn't either. They just say that vulnerability scanning is a technique of security testing that can be used for vehicles. So we'll see how this space evolves, but really just want to say that, again, this is one of those things. It's a high level concept. It often involves multiple tools, and it often involves sifting through a lot of data to understand, what is actually relevant. Okay, the next type of testing referred to in 21434, pen testing. This has been the one that's been around for a long time, but really just want to clarify what that means, because again, one of these things that we get a component supplier that comes to us and they say, hey, can you do pen testing in a week's time? And that's not what pen testing is. Pen testing is this technique of utilizing a team of system experts who understand the technologies, and you actually attempt to exploit the target using any means possible. You do so with differing levels of knowledge against the target system. Usually, the most effective types of pen test are white box pen test, which means you get design information, you get source code, you get a lot of information about the target, and now you're looking at the source code, and then you're looking at it from the actual implementation, and you're trying to figure out what payload could I use to exploit the system. This is kind of like one of the services we run at our vehicle cybersecurity labs we have here in Detroit. We follow a 6-step process. It's nothing special. It's just a organized approach to ensure that our pen tests are consistent. We start with threat modeling, which that means that we're kind of understanding the threats to the system so that we can simulate those threats, meaning we don't want to do things that actual attackers wouldn't do. Then we go through attack surface enumeration and passive recon. We try and understand the system. What types of technologies are in use? We perform some basic scanning to understand basic details about this system. Then we do security defense and protection checks and vulnerability detection. This is the piece where we do kind of basic vulnerability scanning. Active scanning and vulnerability research. We actually start probing the target and try and understand if there are applicable vulnerabilities. We start sifting through those vulnerabilities to see if there's anything we can exploit. The next step, deep testing and attempt to exploit. We use our findings from the previous 4 steps and actually start to attempt to craft payloads to exploit the target. And finally, we sum up all this information into a well-communicated assessment report, such that the component supplier or the automaker we give it to can hand it up ultimately to the auditor, who needs to review this to ensure that that vehicle is in fact secure, whether that's type approval auditor, the automaker, or someone else. Pen testing as a technique may use some of these other techniques I referred to. We may use fuzzing if we think it would be the most effective way to find a way to exploit the target. And we may use vulnerability scanning, like I said. So pen testing tends to combine these other things. It's really whatever it takes to attack the target system within the scope of what we were brought in to test. And then finally, it's an end-of-line check. That's something we just want to say out loud, because it's a form of cybersecurity goal validation. Now, the standard does also refer to it as a technique for verification and not validation as well. But really, you need to think about it as it's an end-of-line check. It's the very last thing you do in terms of security efforts. It's not intended to guide your security design. It's intended to test your security design. I say that because people come to us with pen testing as the first step they're taking towards cybersecurity of a given component or vehicle. But if that's the case, you're approaching this backwards. We're going to miss a lot pen testing. That's not the point. We're not doing, we're going to attempt to exploit the system, but don't treat it as a perfect representation of, hey, every single thing on your vehicle is tested, and if you fix that, there are no other vulnerabilities. So just to be clear, it's an end-of-line check. Where it fits within 21434 is really cybersecurity goal validation. Is your vehicle meeting the goals you designed into the vehicle? Okay, I'll try and run through this because I'm not totally sure how I'm doing on timing here. I know we're running a little bit behind schedule. But what about UNR 155 audit testing? This is an area that's really to be determined. Organizations are starting to figure out how they're going to do type approval audits. A lot of it looks like work product reviews, but we are also seeing nations staff up their own vehicle cybersecurity labs to perform their own forms of audit testing, where they bring in the vehicle, perform some set of tests that feels like a crash test. It's something like, in functional safety, you need to ensure that the vehicle actually, at its production state, crashes into a wall and the airbags deploy. Same thing with this kind of audit testing. There will be some kind of cybersecurity crash test. Feels like it's differing between nations, but it's going to come at some point here as we all figure out what type approval looks like. And then, a lot of this is about redoing that testing. In cybersecurity, it's not one and done. It's not where you can do that crash test, know your vehicle is safe, and you have that 5-star safety rating or whatever it is, and that tends to go on into the future. No, this area changes a lot. The point of 21434, or a big piece of 21434, and the corresponding type approval audit for WP29 is being able to react to vulnerabilities. A new vulnerability comes out, or a new update or a recall comes, or a new update comes out for the vehicle. And then you need to, the automakers and the suppliers need to be able to work together to engineer a software patch or a software update, and then be able to test to make sure that they aren't introducing more vulnerabilities, and ultimately release that update. So it's passing through the V model once again. You need to be able to test quickly, effectively, efficiently. So on the left here, the chart goes through this kind of process of performing your threat analysis and risk assessment to define your requirements. You give those requirements to the component supplier. You work to get those implemented. And then you show those to auditors to make sure that you design that vehicle securely. But like I said, a vulnerability triggers you redoing this, going and looking back at your threat analysis and risk assessment, or performing a vulnerability assessment, defining new requirements, giving it to the supplier if needed, and so on. So that is what it means to be able to release patches quickly for cybersecurity, which is very unlike functional safety, which is what 21434 is modeled after. So from our standpoint, tons of room for automation. That's kind of what gets us out of the bed in the morning. And in the case of verification, that's kind of the piece that we hone in on. What we're looking at is how we can take those requirements. That is the thing that is consistent within 21434, is that you have requirements that need to be verified. Fuzz testing and vulnerability scanning and pen testing, all of those are, like I said, kind of complicated. But requirement verification, it's quite simple. You have a requirement, you document how you would test it, and then you actually test it. And you need to do that over and over again. So what we're working on is developing systems whereby we can set up automated testing to continuously verify that a component or a vehicle is meeting its requirements. And I'm not going to get into too much depth about this, although I could talk forever about it. I just kind of want to show you what that looks like and how we're working with automakers to do that. So on the right here, we're partnered with a company called Keysight Technologies to develop this automotive cybersecurity testing platform. I'm just going to remove the term pen from that because it really shouldn't be there. In that platform, we can write test scripts that can utilize all the interfaces of a vehicle: Bluetooth, Wi-Fi, cellular, CAN bus. There's a cell tower built into this, so we could put a SIM chip that connects up to our cell tower so that we can port scan the connected component of a vehicle. On the left, you see vehicle test bench targets. That's what we're setting up with automakers. Those are those integration test benches. They're modules put onto a piece of wood that then we can control the modules and execute security tests against them, specifically for requirement verification. Just to give a sense for what that looks like in kind of a picture sense, here you can see in the center the pen test platform. On the right is the requirement verification platform we use. We keep track of the requirement status, either passing, unknown, or failing. We have documented the test specification, what needs to be performed. We write a test script that is then pushed down to the equipment in the center, the pen test platform. It executes it against the vehicle test benches, returns the results, and now we have the status for that requirement. We set that on a schedule such that when that vehicle receives a new software update, we understand, is it meeting its requirements? This is kind of how we're addressing that piece of having to redo testing over and over again. And then we aggregate this data so that we can store and export these work products to hand to auditors. We give, this is also useful because we're storing all the status of the cybersecurity requirements or the assurance that a vehicle is meeting its design. That helps decision makers have an understanding of the vehicle cybersecurity at any point during its integration and verification and validation side of the V model. And then we're automating a lot of that work away. So that's where we do a ton of work. Hopefully this was useful in taking some of the terms that you may have seen within ISOSAE 21434, vulnerability scanning, pen testing, functional testing, and then where we work, which is automated requirement verification, and maybe kind of gave some personality or some kind of insight into what that actually means, because we're all going to have to do it. It's in the standard. It's going to flow throughout the supply chain. So yeah, that's it. Hopefully there's time for questions. I actually have no idea. And then we'll move on.
We're going to have to skip that, but please, everyone, if you do have connections or questions, please connect. And I think we'll kind of move and pivot